Hello everybody, this is lecture 7 or chapter 7 in the electronic device book and lecture 7 of the electronic 1 course. I am Amr Abdul Bari with Nearest University. Today I will continue on the amplifiers, but this chapter is focused on the power amplifier. Power amplifier meaning that the signal that you have, it's amplified in the is a large signal amplifier that produce a replica of the signal in the output, okay, but it may be reversed in the reversed signal, okay. And it's defined in which the necessary to consider the problem of the heat dissipation in the amplifier. So there is some a family of the power amplifier. So starting with class A power amplifier, which is a large signal amplifier in which working in the region, the linear region. Here, as you see the Q point here, and you see also that there is a difference between the DC load line and the AC load line. AC load line is between the VCE cutoff and the IC saturation, and the Q point is the same. That's the connection between the center of the AC line and both of them. So the ADC power dissipated is the product of the ICQ multiplied by the VCEQ. Here, this is the power dissipated in the amplifier. So normally the maximum that power delivered is greater or less than 0.5. It's almost 0.25 or 25 percentage, and usually used considerably in the practical application. So we usually use it in the low power application, okay. Question here: what is the efficiency of the amplifier that delivered the 200 milliwatt to the load if the power supply is 12 voltage at 400 milliampere? So as you see here, the efficiency is 6.7, not too much. Now class A amplifier, as you see it here, it's connected to a speaker. So the input, if you see, have the input at 3 voltage V peak to peak is applied to the input. What is the expected voltage at the output? This is a cascaded amplifier. So the power is the V square over the R. So the V square that you have it over the R, so it's 140 milliwatt. This is the power. As you see, as I didn't mention that as before, the common collector, the gain is almost 1, so the output voltage should be identical to the input voltage, okay. For assuming Darlington beta is equal to 10,000, now this is a different so the R input, you see the difference. The R input is here, the R1, R2, beta, RE parallel to RL. So you calculate the R input, and then you calculate the B input, V square over R input, and you will calculate the R output, or the R output is the RL here. It's only the 8. So the power or the amplified or the power gain is the power or the gain of the voltage, which is 1 again, multiplied by the R input over the RL. This is the same equation that we used before in the last lecture. Now let's see, this is approximately 140 milliwatt again. So let's see here another amplifier, push-pull amplifier, use 2 transistors here, this 2 transistor working together, one conduct in the positive cycle and one conduct in the negative cycle, okay. This is, we call it class B. By adding a forward biased diode here, the base emitter drop at 0.7 here, you can doesn't need it to be overcome by the signal, so the signal is connected directly. Okay, this we call it as AB operation or AB class power amplifier. Okay, now this is, you see that both of them are NBN transistor, the same transistor. Now a complementary or identical to or the to the B or push pull amplifier or AB amplifier using a two NBN and BNP transistor. So they connected to in the half of the cycle, half cycle of the input signal. Here, as you see, I used two diodes, so the same idea as you see it in the previously, one for to conduct in the 0.7 and one to conduct for the 0.7 here. So this we call it slight conduction. Okay, so again we use it as a class AB operation. Okay, so it's conducting slightly more than half of the cycle of the input. Okay, now what is the advantage of class AB over class B? The crossover distortion is eliminated, so there is no crossover the 0.7 because of the base emitter voltage. Okay, the drop voltage. Now the AC load line for the NB transistor of the complementary amplifier, push pull amplifier, you see the Q point is here, so the signal is, you see it as this line or this line, so only the one cycle, you see it here, only one cycle is connected. Now the IC is determined by the load resistance, so the IC is equal to VCC over the RL. IC saturation is equal to VCC, this is this value, over the RL. So draw here the AC load line for the NBN transistor. Now as you see here, you should calculate the IC and you have already the VCC. So the VCC is 15. From previous slide, the IC is equal to VCC over RL, so VCC 15 over 30, it's 0.5. The maximum peak output voltage is less than the power supply voltage and the peak, maximum peak. So because the peak at the input, maximum bias current is required, so you can make the peak is larger by using smaller bias resistors, or the beta transistor is higher, such as Darlington transistor. The beta, as you see before, the beta normally is 200, 300. Darlington transistor is 10,000, 20,000 or 5, like that. Although the push-pull amplifier having a good power gain and efficiency, it doesn't have any voltage gain. Okay, so each transistor is configured because it's CC, common collector. Okay, so if we use a Darlington transistors here, replacing the single transistor, here we use two transistors. Okay, so the maximum output is larger than the input because of the Darlington have a higher bias. Okay, as you see here, we use 4 diodes to make the bias here, to equip the bias for each polarity of the input. Okay, now the circuit, yes, I will skip this. As you see here, I give you the concept, I give you the common circuit, I give you the main important idea in the lecture, but learning electronics is by hand, is by calculating the analyze the circuit in the theoretical side, and using simulators to analyze the circuit in practical before implementing in hardware. So this is very important note to understand about education in general. Class C amplifier, here. This is class C. We see class A, we see class B, we see class AB. So much less than 180. This is the conduction, and usually used in the RF application, radio frequency application, oscillators and modulators. Okay, so here the transistor is at when the signal exceed VBB plus VBE, and because the class C are biased for a small percentage of time, they can be very efficient. Okay, so the percentage of time here, it's taken into account. Now if we use it, it's very useful in the oscillator. This is application. So we use a tank here, a parallel resonant circuit as a tank here, coil and capacitor. So as you see here, as the IC go up and down, the IC here, it's, you see the V output is oscillated with the IC, okay, by the short pulses of the collector current. So here again something else, the charge through the base emitter diode is 0.7 here, so less than the positive peak. So you see a cutoff from above here in the output. So this is because of this point here. Now clamping action causes the transistor to be cut off expected at the positive peak. The input, the R1 C1 time need to be long compared to the period of the signal. So that's it. That's why you can see this 0.7 here at this point, and this is the input here. Okay, that's it for today. I speak about let's move this class A power supply. And class A is a type of amplifier that operate entirely in the linear active region. Power gain is the ratio of the output power to the input power of the amplifier. Efficiency is the ratio of the signal power delivered to the load over the power from the power supply of the amplifier. Class B is a type of amplifier that operate in the linear region for 180 of the angle of the input cycle, because it's biased at cutoff. Okay, so that's it for today, and thank you for listening.